Have you ever wondered why a man who lived more than a century ago was still convinced that the entire Earth could be turned into a conductor of limitless power? In the early 1900s, Nikola Tesla stood on the barren ground of Long Island, staring up at a wooden tower with a copper dome, a structure he believed would rewrite the laws of civilization. That tower, Wardenclyffe, wasn't merely an experiment, it was a prototype for global wireless energy, a system designed to transmit power through the Earth itself using resonance, frequency, and a universal vibrational blueprint he believed nature had already encoded into reality. To Tesla, this wasn't madness, it was physics waiting for someone to notice. He saw the planet not as a passive rock in space, but as a vast electrical body humming with natural frequencies. The Earth's crust, the ionosphere, the magnetic field, all of it, to him, was a potential circuit. You, standing anywhere on that circuit, would be able to tap into it the way modern devices connect to Wi-Fi. Imagine the ground beneath your feet serving as a conduit of pure energy, delivered not through wires, but through coherent oscillations, tuned precisely to the Earth's natural resonance. The idea seems impossible by today's engineering standards, yet in Tesla's mind, impossibility was merely a failure of imagination and mathematics. Tesla believed that if you could match the Earth's resonant frequency, you could inject power into the planet the way a singer shatters a glass by matching its vibrational tone. The challenge wasn't generating the energy. Humanity had generators, coal, hydroelectricity, even primitive turbines. The challenge was transmitting it without wires and without loss. At the heart of Tesla's vision stood his concept of the magnifying transmitter, an enhanced Tesla coil capable of creating standing waves that would ripple through the Earth, carrying power the way sound waves move through air. According to Tesla, the Earth rings like a bell. The right frequency doesn't dissipate, it amplifies. Most scientists of his time dismissed this. They didn't believe the Earth could sustain such waves at the scale Tesla proposed. They didn't believe the atmosphere could carry stable electrical currents, and they certainly didn't believe a small number of transmission towers could electrify continents. Yet Tesla kept insisting that the planet already conducted electricity naturally. Lightning, after all, was a global phenomenon. Schumann resonances, fundamental electromagnetic frequencies of the Earth ionosphere cavity, would later be discovered, decades after he predicted them. Tesla insisted that nature left clues everywhere for those who could feel the pattern beneath the chaos. He spoke of energy in abstract but precise language, frequency, vibration, resonance. To many, these sounded like mystical notions, but Tesla didn't use them poetically. He used them mathematically. In his notes, he described the Earth as a charged sphere capable of harmonic oscillation. Power, in this configuration, was not a beam or a ray. It was a synchronization process. If one tower forced the Earth to vibrate electrically, another tower tuned to the same frequency could draw energy from those oscillations. And you, standing anywhere near such a receiver, could harness energy without wires, without fuel, without geographical limits. The idea was breathtaking, but it required the world to believe in a very different model of energy transmission. You may think of power as something that flows through copper. Tesla thought of it as something that flows through nature itself, waiting for engineering to catch up. Whether humanity was ready to hear this or not did not concern him. Tesla wasn't trying to solve the next decade's problems. He was trying to solve the next century's. But engineering reality collided with financial power. Investors wanted wireless communication, not wireless energy. They saw profit in sending messages, not in distributing electricity freely across nations. They funded Tesla's tower expecting radio innovation, not global electrification. When they realized Tesla's ambition was not merely to build a new communication system, but to create an infrastructure that could make selling electricity impossible, the money disappeared. Wardenclyffe fell silent, but Tesla's theory did not die with the tower. The question you face now is simple. Could any part of this vision still work today? Modern physics has validated pieces of Tesla's assumptions. We now understand global electromagnetic cavities, ionospheric conduction layers, geophysical resonances, atmospheric waveguides. We've built prototypes of wireless power systems that transmit energy across small distances using resonance. almost exactly how Tesla described. Our devices already demonstrate the underlying principle. Resonance allows efficient transfer of energy when two systems are perfectly tuned. Tesla simply applied this logic on a planetary scale. Yet, scaling resonance to the size of the Earth introduces complications. The energy required to create meaningful global oscillations might be enormous. The infrastructure to maintain stable resonance would need to be far more precise than anything built in Tesla's lifetime. The Earth's conductivity varies by region, complicating universal transmission. But the most profound challenge isn't the physics, it's the coherence. For Tesla, the entire system had to oscillate as a single resonant body. One interruption breaks the pattern, one mismatch collapses the wave. Still, the concept refuses to disappear. Engineers continue to revisit it. Theoretical physicists revisit the math. Energy researchers examine new conductive materials and atmospheric properties. You stand in the same position as those who saw Wardenclyffe rise, wondering whether the world was simply too early for what Tesla tried to build. Perhaps timing matters more than technology. Perhaps Tesla's understanding of energy, frequency, and vibration was not wrong, only out of phase with the capabilities of his era. Whether the idea awaits rediscovery or final dismissal remains uncertain. The tower may have crumbled, but the physics has not. The vision of the Earth as a colossal resonant instrument did not end with the collapse of Wardenclyffe. Instead, it evolved into a scientific riddle that continues to haunt researchers. Once the initial spark of Tesla's proposal is understood, the next question naturally emerges. What physical principles would be required for global wireless energy to function in practice? To understand this, one must step deeper into the world Tesla inhabited, a universe where electromagnetic fields were not merely forces, but structures, where resonance was not a metaphor but a governing law, and where the boundaries between engineering and cosmology were thinner than society believed. The core of Tesla's approach relied on exciting standing waves within the Earth itself. Standing waves are unique because they do not travel the way ordinary waves do. They oscillate in place, forming stable nodes and antinodes, areas of destructive and constructive interference, shaping patterns that persist as long as the driving frequency remains coherent. If you were to tap into one of those stable points, you could, in theory, draw energy without being physically connected to a generator. The generator would interact with the Earth's conductive layers, and the Earth would respond like a tuning fork struck at its natural pitch. Tesla's magnifying transmitter was crafted to exploit this phenomenon. Unlike a simple Tesla coil, which creates high-voltage arcs for local demonstration, the magnifying transmitter was designed to inject electrical oscillations into the Earth like a needle delivering current into a bloodstream. The system depended on three interlocking elements: the electrical impedance of the Earth, the resonant frequency of the transmitter, and the ability to sustain oscillations long enough for energy to accumulate globally. In Tesla's calculations, once global resonance was achieved, minimal input power would be required to maintain it. He believed the Earth's natural conductivity would reinforce the wave rather than resist it. However, modern measurements complicate this optimism. The Earth is not a uniform conductor. Its lithosphere contains metals, silicates, crystalline structures, and varying moisture levels. Conductivity differs between continents, oceans, deserts, and volcanic regions. Yet even with this variability, the Earth can still support extremely low-frequency waves, LF waves, that propagate with minimal loss across the globe. The existence of Schumann resonances, electromagnetic standing waves trapped between the Earth and the ionosphere, proves that planetary-scale resonance is not theoretical, but inevitable. Tesla predicted these resonances decades before they were measured. He described the Earth as a sphere of electrified particles whose vibration can be manipulated. Later, physicists would discover that Earth's resonances sit around 7.83 Hertz and several harmonic frequencies, all aligning eerily with Tesla's early assumptions. The question then becomes, if global resonance exists for natural electromagnetic waves, could engineered resonance exist for human-produced power? This is where the limitations sharpen. While Schumann resonances operate at extremely low frequencies, Electrical power distribution requires much higher frequencies to be practical. The energy density needed to transmit usable electricity without wires would demand far stronger fields than nature produces on its own. Tesla believed that by magnifying electrical oscillations through his transmitter, these energy densities could be reached safely and efficiently. Critics argued that the required energies would ionize air, disrupt communication systems, or produce unpredictable atmospheric effects. Tesla countered that coherent resonance would prevent losses, and that the system's efficiency would rise dramatically once global oscillation stabilized. Modern simulations show mixed results. On the one hand, global resonance is theoretically possible. The mathematics does not forbid it. The Earth can carry electrical waves, and if oscillations are introduced at precise frequencies, amplification can occur. On the other hand, the energy required to initiate global resonance at useful power levels might exceed the output of entire national grids. The infrastructure to maintain perfect tuning would need active feedback systems monitoring planetary conductivity in real time. Yet, even this objection does not fully collapse the idea. Technologies now exist: superconductors, ultra-high efficiency resonant circuits, precision waveform generators that Tesla could not access. Where he relied on copper, iron, and wood, modern engineers can use quantum materials, computational feedback loops, and adaptive frequency stabilization. If Tesla were to examine today's atmosphere, he would find a world saturated with signals: radio, microwave, satellite communication, Wi-Fi, cellular networks. Ironically, all these systems operate using principles he pioneered: high-frequency oscillations, tuned receivers, resonance-based transmission. They represent fragments of the world Tesla imagined, though scaled down to information rather than energy. The infrastructure for global communication is, in many ways, a miniature reflection of the global energy web he once proposed. Humans now live inside a vibrating electromagnetic shell Tesla predicted before the first radio station existed. Yet the barrier between transmitting information and transmitting power is enormous. Information requires negligible energy. Power must deliver massive energy density. A message can ride on a whisper, a continent cannot. This distinction often becomes the central argument against Tesla's dream. Still, resonance complicates the debate. When a system is tuned, the required input drops dramatically. Even a small push can create a large response if the frequency aligns perfectly. Tesla understood this deeply. He believed the Earth, once synchronized, would maintain oscillation with minimal input. Modern researchers exploring wireless power transfer at smaller scales continue to confirm coherence-based amplification effects. Wireless charging pads, resonant inductive systems, and mid-range power transfer devices all depend on versions of Tesla's principle. The psychological resistance to Tesla's global system comes not from physics alone, but from its implications. A world powered by a single global oscillator challenges political structures, economic models, and corporate monopolies. Energy independence, in Tesla's view, wasn't about nations drilling or mining. It was about understanding the physics of the planet itself. When energy becomes a property of nature rather than an extractable resource, the power dynamics of civilization shift. In Tesla's lifetime, this was unacceptable. Today, entire industries would resist it for the same reasons. Sometimes ideas fail, not because they are wrong, but because the world surrounding them is not prepared for the consequences. Even so, the concept lingers. It resurfaces in academic papers, fringe engineering labs, atmospheric physics studies, and alternative energy research. The persistence of the idea reflects something deeper: humanity's recognition that the existing electrical infrastructure is fragile, resource-dependent, and geographically constrained. The idea of Earth-based resonance survives because it answers a question modern systems cannot: how to distribute energy without wires, without distance limitations, and without loss dominating the equation. As you attempt to understand whether Tesla's global wireless energy system remains physically possible, the world does not offer a simple yes or no. Instead, it presents a spectrum of partial truths, feasible principles, impossible scaling challenges, verified predictions, untested assumptions. The puzzle remains open. And somewhere within that open space lies the boundary between physics as understood and physics as unexplored. When exploring the final and most controversial layer of Tesla's ambition, the narrative inevitably shifts toward the boundary between theoretical physics and technological feasibility. At this depth, the idea of global wireless energy transforms from an engineering challenge into a question about the nature of the universe itself. Tesla believed the cosmos was built on systems of recurring patterns, oscillations, harmonics, and fields that repeat from the microscopic to the planetary scale. To him, energy wasn't merely a resource, but a structural property of reality. Understanding how to move it, tap into it, or amplify it meant understanding the hidden rhythms that bind the physical world together. From this perspective, Tesla's global energy system wasn't just a power grid. It was an attempt to synchronize human technology with the natural frequencies of the Earth. If the planet acts as a conductor, and if the ionosphere forms a resonant cavity above it, then a properly tuned transmitter could couple these layers into a single oscillating system. Once the system locks into resonance, the flow of energy becomes governed by wave mechanics rather than by traditional electrical transmission. Distance becomes irrelevant, losses reduce dramatically, and the entire globe becomes part of the circuit. This is the central mechanism Tesla envisioned, a state of harmonic coherence between the Earth, the transmitter, and the atmosphere. In this synchronized condition, a tower would no longer be broadcasting electricity outward. Instead, it would be shaking the entire Earth ionosphere cavity electrically, the way a musical instrument vibrates when struck. Any receiving device tuned to the same frequency could extract energy from those oscillations, in some cases even amplifying the local wave strength due to constructive interference. This is why Tesla always emphasized resonance over brute force. To him, the universe favored systems that speak the same frequency, but achieving coherence on a planetary scale requires extraordinary conditions. Modern analysis shows that the Earth's conductivity, though sufficient for natural low-frequency resonance, is immensely complex. Oceans conduct more efficiently than land. Mineral-rich regions differ from desert regions. Underground water channels change impedance unpredictably. These variations act like distortions in an otherwise clean signal. For Tesla's system to work, the transmitter would need real-time calibration to match Earth's shifting electrical behavior, a task that would have been impossible with early 1900s technology. Today, however, adaptive resonant systems exist. Computers can measure microfluctuations in real time, adjusting frequencies and phase alignments with precision far beyond Tesla's reach. Then comes the atmospheric component. The ionosphere, a charged shell of particles surrounding Earth, naturally carries electrical currents, most notably through atmospheric phenomena like lightning and auroral activity. Tesla believed the ionosphere would assist in power transmission by forming an additional conductive layer. Modern data supports parts of this view. The ionosphere is indeed a massive electrical conductor, and ELF/VLF waves can propagate through it over vast distances. But using it deliberately for power transmission introduces challenges. Solar storms, geomagnetic fluctuations, and atmospheric density changes affect conductivity significantly. Tesla assumed nature would maintain stability through self-regulating mechanisms. Modern science shows nature does maintain patterns, but not always with the reliability needed for industrial energy distribution. Even with these obstacles, nothing in the known laws of physics strictly forbids the mechanism Tesla proposed. The challenges are logistical, energetic, environmental, and political, not fundamental. The magnitude of energy needed to initiate global resonance remains contested, but with advanced pulse generators, superconducting materials, and global feedback networks, the energy cost might be far lower than once assumed. Experiments in controlled resonant energy transmission continue to show that small, coherent inputs can produce disproportionately large effects when systems are properly tuned. What complicates the conversation most is that Tesla's system demands a mindset shift. It is not a power line. It is not a radio broadcast. It is not a microwave beam. It is a resonant coupling between technology and the planet itself. That coupling requires precision, stability, and a philosophical acceptance that energy is not something humans own, but something they synchronize with. This is where the scientific and spiritual sides of Tesla merge, not in mysticism, but in a recognition that physical systems often behave like musical instruments. Harmony matters. Phase matters, alignment matters. This vision clashes with the infrastructure humans have built. Modern electrical grids rely on predictable transmission lines, transformer stations, regional isolation zones, and controlled distribution networks. Global resonance, by contrast, is collective by nature. One transmitter affects all receivers. One disturbance affects the entire oscillation. From an engineering standpoint, this creates vulnerability. From Tesla's standpoint, it creates unity. He saw energy as something humanity could share if it aligned with nature's own structure. He viewed the Earth as alive with electrical movement, and he believed the role of technology was to amplify what nature already provided. Even if the system were physically possible, its implementation would face immense resistance. A global energy web undermines the economics of centralized production. It erases the concept of selling electricity by the kilowatt hour. It eliminates energy monopolies. It renders wires, pipelines, grids, and fuel irrelevant. The shift would be equal to dismantling the economic foundation of the industrial world. This is why Tesla encountered opposition. The physics was arguable, but the implications were unmistakable. Global wireless energy would democratize power in a way no government or corporation would willingly permit. Despite this, the idea's persistence suggests something important. Humanity intuitively recognizes that the current system is not the final form of energy distribution. There is too much loss, too much infrastructure, too much fragility. Tesla's proposal hints at a different paradigm, one in which the Earth becomes part of the engineering solution rather than something to drill into or build over. Even if the exact architecture he envisioned never materializes, the principles behind it continue to influence modern research. Resonant transfer, adaptive frequency control, planetary scale electromagnetic modeling. These fields are expanding. Each discovery brings the scientific world a little closer to the territory Tesla explored with pencil, paper, and intuition more than a century ago. The lingering question is not whether Tesla was wrong, but whether humanity has ever attempted to fully test his vision with the tools available today. And until that test is performed, the question of global wireless energy remains open, suspended between theoretical plausibility and practical impossibility, waiting for an era bold enough to attempt coherence on a planetary scale. What if the system fails not due to physics, but due to the instability of human-made oscillatory infrastructures that cannot maintain global phase coherence under fluctuating terrestrial impedance?